Hello students, welcome to Akshara Air Foundation. So today we are going to start the new chapter, that is Newton laws of motion. Okay. So in the first class in the kinematics we have studied about the motion of the object, and we have seen the relation between the different physical quantities of the motion of the object. Okay. By the equations of motion we have seen that there. Okay. And motion in a plane, how the motion of the body in the straight line motion, how it will be in the plane, that we have seen there. So now here, and in this Newton laws of motion, we are going to discuss the cause of the motion of the body there. Okay, what causes the motion of the body? In the first lesson in kinematics, we have seen there. So only the motion of the object and relation between the physical quantities of the object we have seen there. Different physical quantities like velocity, acceleration, displacement, and time there. Okay. So, but we didn't consider there, we did not study about the cause of the motion of the body. Okay. So, here in this Newton laws of motion, so this will be come under the dynamics. Okay. This Newton laws of motion will be come under the dynamics. Okay. Instead of dynamics, we are saying here Newton's laws of motion, because the Newton has done the many experiments and he observed the universe and many objects which will be behave on the planet there. So, and he given the cause of the motion of the body there, okay, and he measures and he given the equation. About that we are going to discuss in this chapter. Okay. So then we'll see by the what laws he has explained the motion of the body and cause of motion of the body, what it affects this cause of motion of the body, that is nothing but a force, how the force will be affect on the objects, okay, movement of the objects there, that we are going to see here now. So Newton's laws of motion, Newton laws of motion, Newton's laws of motion. By observing the by observing the nature, he has done many experiments with the different objects, and he concluded that so three laws, they are well known as the Newton's laws of motion. So first one is Newton's first law of motion. First law of motion. It is also called as law of inertia. It is also called as law of inertia. Okay. So law of inertia. In the nature, all the objects, see generally, if the object is there at the at certain position there, it will be at that position only until some external force, until any action will be takes place on the body, that body will be stay at its position there. Okay. So suppose the body is in the motion there, the body will be continuous its motion unless until some external force applied on it there. Okay. So by that observations, so here is given the statement. So that statement is nothing but the statement of Newton's first law of motion, until and unless an external force applied on a body will be in its state of rest or uniform motion. State of rest or uniform motion. Rest or uniform motion. Rest or uniform motion. Okay. So general here they have said the word there, rest and uniform motion. Uniform motion. Rest and uniform motion. With these two terms. See Galileo, Newton to discover this laws. So Newton has done many experiments done by the Galileo. Okay. So Galileo has said that so generally the nature of the body will be rest or uniform motion. So rest or uniform motion, he has said there. So then So by doing the experiment done by observing the experiment done by the Galileo, so Newton has done some more experiments, and he concluded with this statement, that is, until and unless an external force applied on a body, the body will be in its state of, and a body will be in its state of rest or uniform motion. Okay. So means if a body will be come into the motion when the force is applied on it there, or the body come into the rest if the external force applied on it there. So based on the applied force, whether the body has to be move or whether the body has to be stopped there. Okay, that will be takes place there. So we can see there in our day-to-day life, there are the many objects always they will be at the rest. So until some external force applied on the body, then it will be stay at that position only. Okay. So that is the property. It gives the property of the inherent property of the body there. Inherent property of the body. So that property of the body is said as inertia. Okay. So now this Newton first law is also known as the law of inertia. It is also known as law of inertia there. Okay. So what is that inertia? It is the nature of the body there. Nature of the body. Inherent property of the body. By the nature, by itself. So it has that nature there. That means the body will be, it continues in its state of rest or uniform motion there. Okay. So suppose here we can say that inertia. Okay. So inertia, so it can be defined as the inability of a body to change its state of rest or uniform motion. Okay. The inability of a body, or the tendency of a body to change its state of rest or uniform motion there. Okay. It does not want to change its state from its original position there. It tries to be stay at that position only. Okay. Whenever the external force is applied there, anything, the cause of motion of the body changes its direction there, its motion, or if it is try to change, then the body will be remain in its state of rest there. Whether it may be in the rest, it tries to be in the rest only. If the body is in the motion, it tries to be in the motion only there. So that nature of the body is called the inertia there. So it can be defined as, so the inability of a body, the inability of a body, the inability of a body, inability of a body, inability of a body to change its state, of rest or uniform motion, rest or uniform motion by itself, uniform motion by itself. Okay. The nature, any object, okay, it cannot be changes its position by itself there. Okay, it's stay in its position only. It does not want to changes the position of the body there. So that nature of the body, that property of the body is said to be the inherent inertia there. Okay, it is the inherent property of a body to change its state of rest or uniform motion by itself. Okay, so that is called this inertia. It will be three types there, and this inertia will be depend on the mass there. Okay, mass of the body there. So inertia can be measured by the mass of the body there. If the mass of the body is more, inertia will be more there. Okay, so this inertia, it is so we write the mass of an object is the measure of inertia. So inertia, it is a not a physical quantity, just it is a property of a body there. Okay, so property of a body there. Then that inertia can be measured by the mass of the body there. If the mass is more, then inertia will be more there. Suppose we can say there it is very easy to move this object from here to here there, or from on the floor if it is placed there, and it is easy to move from change the position of this body there. Okay, if the body has a more weight, suppose if you keep a brick there. Okay, so to change the position of the body, so from its position, then we need to apply more force than this body there. How much force we apply to move the body? So then greater than this force, we need to apply the force on the greater mass of the body there, so that the position of the body will be changes. Why it is? Why? Because there is a inertia of the body is more there. If it is a more mass, then more inertia it will be higher. That means it does not changes its position by itself. Okay. So even if you apply the external force, there the more effort has to be needed to bring the body into the motion there, or even it will be applicable for the motion also. If the body is in the motion, then it is very difficult. If heavy mass of the body, so it is very difficult to bring it into the rest there. Okay, so means there is a huge amount of effort has to be place, so that then the body will be coming into the rest there. Okay, so mass is the measure of inertia. Then SI unit, here we can write there, then SI unit of inertia, SI unit of inertia is kg, we can add there, kg. Okay, SI unit of inertia is kg, we can add there, because it is measures by the mass there. Okay, then this is there are different types of inertia there. Types of inertia. Okay, so they are the first one is inertia of rest, and second one is inertia of motion, and the third one is inertia of direction there, inertia of direction there. So now inertia of rest is nothing but the inability of a body to change its state of rest by itself is called the inertia of rest, and inertia of motion is nothing but the inability of a body to change its state of motion by itself there. So whenever the body is in the motion there, so it does not want to change the position of the body of its motion there. Okay, it is external force has to be applied on the body, then only it will become to the rest there. If it is applied there, then there are the different consequences will be takes place there. Even it is if the body is at the rest, means if it is stationary, then it does not come by itself into the motion there. Okay, so there is a external effort has to be takes place there, then only it will be coming into the motion. And inertia of direction, even the direction, so the body if it is moving, okay, so in one direction, if a body is moving in one direction, then it will not move by itself. So the direction of the body has to be changed, means there is a external effort has to be takes place there, then only the direction of the body will be changes there. Suppose a body is there in its direction, in a particular direction there, so it does not want changes its direction there, that is called inertia of direction. Okay, means the inability of a body to change its state of direction is called by itself is called the inertia of direction. See here we will have the example, the consequences we have for this inertia of rest. Suppose if tree trunk has shaken, okay, or tree branch has shaken there, some of the leaves will be fall, and the fruits also will be fall there. Why? Because there is an external force applied on the body. Before that the body is at the rest there. Okay, the body tries to be, all the fruits and the leaves will be tries to be at the rest, but the externally certain forces applied there, so they will be not cope up with that force, cope up with that motion of the body, so that they will be fall there. Okay, suppose any on glass tumbler, if you place a cap there, over that any coin is placed, then if you drag it suddenly, then the coin will be fall in the glass tumbler. Okay, that is because of the inertia of rest. Even the dust particles also come out from the carpet, that is because of the inertia of the rest there. Or suppose you get into the bus and bus suddenly starts there, then all the passengers or we people will be fall backward on the seat, okay, onto the seat there. That is because of the inertia of rest. The body tries to be at rest, but it is suddenly coming into the motion, then suddenly it does not changes its position there. So in the consequence of that, then the body will be moves backward and it will be fall backward there. All the passengers in the vehicles, if it is started suddenly, then they will be fall backward onto the seat there. That is because of the inertia of rest and inertia of motion. So whenever the body is in the motion already, then if it is comes to the rest suddenly, then all the passengers will be fall forward there. Okay, that is because of the inertia of motion. Okay, so the next inertia of direction there. Inertia of direction means, suppose if a body is, suppose the vehicle is turning left side, then all the passengers in the vehicle, they will be lean rightward because of the inertia of direction there. Okay, whenever the direction is changing there, so the changing direction cannot be, the body itself, it cannot be changes its direction there. Still it will be in its state of rest, so that if it is turn left side and the body will be in the right side only, it will be moves right side there. That is because of the inertia of direction. So we can see the, if a bicycle or a bike is moving, okay, in the mud water, then what happens there? All the mud water will be comes along the tangential direction of the wheel of the vehicles there. Okay, all the mud water will be fall on the riders, the passenger there. That is because of the inertia of direction there. Even any object is a stone is tied to the one end of the thread and other end is kept in our hand, and if it is rotated horizontally or vertically, then the stone will be move in a circular path there. Okay, suddenly if the this hand has removed, the thread has removed there, then how it will be go there? Along the tangent, in a circular path, along the tangent, the body will be move there. Okay, because suddenly there is a force is removed there, then it will be move in the same direction there. It will be the direction every time. The direction of the body is changing every time. Direction of the motion is changing. No, then suddenly the force is applied. It is removed there. There is no centripetal force act there. Centripetal force is 0. Then it will be move away from the along the direction of the tangent of the circular path. It will be moved there. Along the direction of the velocity, it will be moved there. So they are all the examples of this inertia of rest and inertia of motion and inertia of direction there. Okay, so this is about the inertia. Okay, now this first law, Newton first law, is explains about the quality of the motion, and it is explain about the force. So Newton, now this first law, this law explains about force, about force and inertia, about force and inertia. About force and inertia, and it explains the motion of the body. It explains the motion of the body. It explains the motion of the body. Motion of the body. Motion of the body qualitatively. Qualitatively. Okay. So this is about the Newton's first law there. Okay, next law we are going to see there. Before going to see the Newton's second law, we will be learn some of the definitions. Okay, that is linear momentum. So linear momentum. So linear momentum is nothing but the product of mass and the velocity. So this is nothing but the quantity of. It explains about the quantity of the motion of the body there. Okay. If a m mass of the body is moving, okay, with certain velocity v, then the momentum or the quantity of the motion of the body, it is said by the linear momentum, that is nothing but the mass and the velocity there. It is, so simply it can be defined as the product of mass and the velocity of an object is said to be the linear momentum. Okay, it is a vector quantity. Linear momentum is a vector quantity because velocity is also vector quantity. So then SI unit, what can I write here? So SI unit of linear momentum, SI unit of linear momentum P, SI unit of linear momentum P is given by, from its formula we will get now kg meter per second, kg meter per second, that is a kg meter per second. Okay, and second one we can write here. Second one, dimensional formula of P is, what can we write here? M power 1, L power 1, T power minus 1. So from the SI unit we can write now kg meter per second. Kg symbol is m and meter symbol is L, and the here S symbol, time symbol is what there, here T, no, capital T. So here powers will be per mass it is 1 and per length it is 1 and for the time it is -1, powers are, okay. So that is the dimensional formula of the linear momentum there, okay. So then change in momentum, suppose the body is moving, there is a change in momentum will be there, that change in momentum can be written as change in momentum, change in momentum. Change in momentum can be it is denoted by the delta p. Delta p is nothing but, so it is the difference of final momentum and the initial momentum. Okay, so that is, we can write here p final minus p initial is called the change in momentum of the body there. Suppose if a body is moving, so m of mass m, initially it will be have the velocity u, and after before going to the rest, the body will have the final momentum v. So then the change in momentum can be written as here delta p is equals to here mv final minus mu initial, or we can write there mv initial, or we can write here m into v final is nothing but v will write there, and u v initial is nothing but u we can write there. So therefore delta p is equals to m into v minus u, m into v minus u, okay. That is the change in momentum, change in momentum there, okay. So change in momentum is also has the same units as the this linear momentum there, okay. So linear momentum, how can we define it? Is it can be defined as, it can be defined as the product of mass and velocity of an object, mass and velocity of an object, is called, that is enough. Okay. So this is the definition of the linear momentum, okay. So now we are going to see the Newton's second law, Newton's second law. So Newton's second law will explains the measurement of the force there, okay, how the force will be act on the body there, and if the force is acted on the body, then how that momentum, how the quantity of the motion of the body will be takes place there. So it will be give the relation between the force and the momentum there. So the statement of this is the rate of change of linear momentum, rate of change of linear momentum of an object is directly proportional to the external force applied on the body there, external force applied on the body, external force applied on the body, and it is in the direction of, and it is in the direction of applied force, okay. So this is a statement of Newton's second law. The rate of change of linear momentum is directly proportional to the external force applied on the body, and it is in the direction of the applied force. Suppose let us consider this is the body is there. If you apply with low external force, less value of external force, then the momentum will be slow there, okay. If I apply large force, then large force it is applied there, the momentum will be a little bit fast. Okay. So then how much force you applied there, that much momentum of the body will be there. Okay. So then here, so this external force, F external force is directly proportional to from the statement. So we can remember by using this equation, mathematical expression, we can remember this whole statement like here dp by dt. So d means differential momentum, means small momentum, small change in momentum in the small interval of time there. So d will be said as differential equations. We have learned now d, change in small change, okay, difference in the momentum there. So this is the expression for the mathematical expression for the Newton's second law there. Okay, the external force applied on the body, the rate of change of linear momentum is directly proportional to the external force applied on the body. So if this directly proportional in the sense that here the force is increased, force is changes and momentum also will be changes there. If force is increased, momentum also increases, and force is decreases, momentum will be decreases there. That is the directly proportional to the external force there. Okay. So from this, if you write here like this, if you want to remove this proportionally, we will get a constant, that is a k into dp by dt, we can add there dp by dt. So from the momentum, so what is the momentum p value, what can we write here? So F external is equals to k into d into mv divided by dt. Okay. So m is a constant there. So when the force is applied, when the body coming into the motion there, mass of the body does not change, mass will be constant. If it is a constant, it can be come out from the differentiation, that dv by dt will be there. We know dv by dt is nothing but what there? Instantaneous acceleration. Rate of change of velocity is called there acceleration. No? So instead of this, we can write here. So since a is equals to dv by dt, no? Since a is equals to dv by dt, so therefore here F external can be written as here k into m into a, we can add there. Okay. Suppose if here m is equals to 1 kg mass of the body is moving with the 1 meter per second square acceleration, then the force acting on the body is said to be 1 Newton. Then so the k value, so k is equals to, it is given 1, k is equals to 1 there. So if k is equal to 1, then F external is equals to will get there. So m into a will get there. So this is the expression for the force acting on the body there. So F is equal to m into a. So this is the expression for the force there. F is equals to m into a, mass into acceleration. F is equal to mass into acceleration. Now the force can be defined as, so in lower studies we have studied there, force is nothing but push or pull of an object is said to be the force. Okay, that force, that action, the action which changes the motion of the body or changes the shape of the body, or we can say there changes, increases or decreases the speed of the body, changes the direction or the shape of the body. Okay, so that action is said to be the force. Then how it has defined? So it has defined by this Newton's second law. By the Newton, he is given that force is equals to mass into acceleration. It is the product of mass and acceleration of the body. Okay, it is the product of mass and acceleration of the body. Okay, that is said to be the force. So now we'll see about the force there. Okay, force. So force is defined as, it is defined as the product of mass and acceleration of an object is called of an object. Okay, that is enough. Okay, it is a product of mass and acceleration. So the force can be denoted by the letter F, and mass is it is nothing but small m, and acceleration of the body is a here. So F is equal to m into a will be the expression, formula, mathematical expression for the force. So then SI unit of this one. So SI unit of force. SI unit of force can be written as here what there. Mass into acceleration. Now mass is measured in kgs, and acceleration will be measured in meter per second square. So kg meter per second, this is said to be the 1 Newton, or we can write here Newton. Okay, how can we define a Newton then? Okay, so if 1 kg of mass of body is moving with the 1 meter per second square acceleration, then the force acting on the body is said to be the 1 Newton. Okay, so that is the definition of the Newton. And now here dimensional formula of force is dimensional formula of force. How can I write there? Kg. So kg means here mass m power 1, L power 1, T power minus 2. There is a dimensional formula. So then this force is a vector quantity because the acceleration is a vector quantity. Any scalar, mass is a scalar quantity. If the scalar is multiplied by the vector, then we will get a vector only. So the force is a vector quantity. It is a vector quantity. It is a vector quantity. Force is the vector quantity. Okay, that value may be positive or 0, or it may be negative also. Okay, then this is about the force. Okay, so now here this Newton's second law will explains the Newton's second law. This law explains the measurement of force and linear momentum linear momentum. It explains about the linear momentum and the force. It measures the force. It will give the force definition, okay, and the expression. Okay, next we will see there. Next one is next law. Next law is the Newton's third law. Newton's third law. So for every action there is an equivalent and opposite reaction. That is the well-known statement of Newton's third law. So for every action there is equivalent and opposite reaction. Action is equals to minus of reaction. So action is equals to minus of reaction there. Okay. Suppose we can take the example as like if a ball is thrown onto the wall there. Okay, throwing a ball means ball will apply the force on the wall, and at the same time wall is also apply the force on the ball there. So then this equal force, equal in magnitude, with how much force you apply on the apply by the ball onto the wall there. So the same force it will be applied by the wall on the ball there, so that it will be rebounds back. Okay, so that is because action and reaction. So pair of forces, when this action and reaction will be takes place there, these are said to be the pair of forces. These pair forces will be act on two different objects there. So these two will be not act on the same body. So both will be act on different bodies. These pair of forces, they are nothing but action and reaction, or acts on two different bodies, different bodies there. So in the same example, ball and ball example, if you take there, ball will apply the force, that is the action, and in the reaction the ball will apply the force on the ball there. Okay, on two different, and it will be in the opposite direction there, equal in magnitude and opposite in direction there. So that is the Newton's third law. Pair of forces will be act there. So the examples for Newton's second law, we can write here. The recoiling velocity of the gun is also example of this one. Newton's third law. The propulsion of rocket. The rocket will be going to the space due to this Newton's third law only. This Newton's third law will explains the law of conservation of linear momentum. Okay, it explains the law of conservation of linear momentum. Okay, what is law of conservation of linear momentum? We'll see there. So simply we'll write here LCLM, law of conservation of linear momentum. So if there is no external force acting on a body there, if there is no external force acts on a body, the body remains in its, if there is no external force, only the internal forces will be acted there then, okay, and a body or any system there. So then the total momentum of a body is remains constant, is said to be the law of conservation of linear momentum, okay. If there is no external force, suppose from the second law of motion we got the equation like this, no, dp by dt, k into dp by dt there. If there is no external force means what there, this f is equal to 0 there, okay, f external will be 0 there, k into dp by dt will get here, dp by dt. So from this what can you write here, dp is equals to, if you send dt that side, dp will be, that is equal to 0, no, dp is equal to 0, dp is nothing but what there, change in momentum. Change in momentum is nothing but final momentum minus initial momentum, final momentum minus initial momentum, that is equals to 0. So then here we will write there initial momentum is equals to final momentum. So that means what there, if there is no external force act on the body there, so there the total momentum of the body is conserved or constant. Conserved means constant there. So means before the action and after the action, the total momentum of the system or a body is remains constant, is said to be the, or we can say that the change in momentum. The change in momentum will be 0. Okay. So that is said to be the law of conservation of linear momentum. So we can take the example of recoil of gun there. So before the gun fires, when the gun is loaded with the bullets and before it fires there, the total momentum of the body, momentum is nothing but what there, mass and velocity there. So after loading, the gun will be at the rest only. There is no motion, velocity of the motion of the bullet and motion of the gun will be takes place. When you fire, when you trigger it, then the bullet will be come out with certain speed and it has certain mass there. So the momentum will be there. At the same time, the gun is also, it will be gives the backward jerk when the bullet is coming from the gun there. So that is due to the internal forces of the gun there. There is no external force acts on it there. Okay, that is nothing but the example of law of conservation of linear momentum, or we can take here the Newton's third law also. Okay, so here the external force is 0, then change in momentum will be 0. Change in momentum will be 0. Change in momentum will be 0 means the total momentum of the system or a body is conserved. Before action or after the action, the total momentum will be conserved, constant there. Okay. So from this we will get the recoil. Here we will discuss the examples of this Newton's law of conservation of linear momentum or Newton's third law. So if a gun fires there, the total momentum, initial momentum can be taken as here P initial is 0 and final momentum what we can take there, mass of the bullet is small m, we considered there, and velocity of the bullet is small v, and plus mass of the gun is capital M and velocity of the gun is capital V, we can add there. Okay. So now according to the law of conservation of linear momentum, so this one, the total momentum will be constant there, initial momentum is equals to sum of the total momentums acting on the system. Okay. Initial momentum will be 0 and here total momentum is what there, that is the after the gun fires, this is the momentum of the body there. So that is mv plus capital M into capital V. Okay. So then here we can add there minus m into v is equals to capital M into v there. So from this what can we write here, this is the velocity is the velocity of the gun there, we will get here minus mv divided by capital M. So this will be the recoiling velocity of gun. So here v is said to be the recoil velocity of gun there, recoil velocity of gun. Okay. So this is a small m will be the mass of the bullet and small v will be the mass of the velocity of the bullet and capital M will be the mass of the gun. Okay. So capital V will be the recoil velocity of the gun there, This is example for the Newton's third law, or we can say law of conservation of linear momentum. Even the propulsion of rocket also. So rocket is moving up there, the ejection of the gases will be applies the force downwards, then there is a upthrust will be created, then due to that upthrust the rocket will be moves into the space, okay, with large force. So that is they are the example of this Newton's third law, law of conservation of linear momentum. Okay. So next one we are going to see here So while we are discussing this Newton's laws of motion, then we should discuss about the okay. Here we should discuss about the inertial frame and non-inertial frame there. Okay. So frame of reference. Next concept is frame of reference. So next one we will see here frame of reference there. Frame of reference. Frame of reference. Frame of reference. So there are two types of frames of reference here are there. So inertial frame of reference, inertial frame of reference, frame of reference, and non-inertial frame of reference there. Second one is non-inertial frame of reference. Non-inertial frame of reference. Non-inertial frame of reference there. So inertial frame of reference is nothing but the frame of reference in which the Newton laws of motion applicable, Newton's second law, it can be applicable. That is called inertial frame of reference there. The non-inertial frame of reference is nothing but the frame of reference in which the Newton's second law or the Newton laws cannot be applied. Okay, it is called the non-inertial frame of reference there. So we can take the example of if a body is, suppose motion of the body on the ground there. Okay, motion of the body on the ground or motion of a body in the lift. We can say the lift will move up and down. No? So whenever it is moving with constant velocity, then we can say that is the example of reference frame there. Okay, if it is moving with different velocity, then so it will come under non-inertial frame there. So motion of the body, even the motion of the vehicles, a bus or lorry, anything, the vehicles which are moving with constant velocity, then we can say that frame of reference, bus, train. So they are said to be the inertial frame of reference there. If they are moving with different speeds, then it will become under non-inertial frame of reference there. Suppose the lift is there, you will be traveling the lift up and down. Then it will be, if it is moving with different speeds, the different speed means acceleration will be different. No, it will be under the gravity, uniform acceleration. So in that case, so there is a motion of the body will be different there. In that cases, we cannot apply this Newton's second law. Newton's laws of motion we cannot apply in the non-inertial frames there. To apply that, so we need to introduce the pseudo force. Okay. Pseudo force, or we can say this is an imaginary force. Imaginary force, pseudo force or imaginary force there. So it is nothing but this will be equal to the change in the forces acting on the body there. Okay, imaginary force or pseudo force, it is the changing the force, or we can say the net resultant force. It is the pseudo force will be equal to the net resultant force acting on the body there. When there are multiple forces acting on the body, then the net force acting on the body will be equal to the pseudo force, that is due to the acceleration of the frame. So in frame, reference frame is nothing but we have said it is a background now where the body is studied there, motion of the body is studied there. Okay, it is a reference frame. If it is a constant, that reference frame is constant, then we can describe the motion of the body by using the Newton laws of motion. Okay, but whenever the reference frame is moving, okay, so with respect to the ground, then it is difficult, no? So to apply this Newton's laws, so then to apply this Newton's laws, there they have considered their pseudo force. The pseudo force is nothing but the force due to the acceleration of the reference frame. So then we'll get the pseudo force. That pseudo force, the force of the, if it is the reference frame is it is in the motion there, then it will be have certain acceleration and the mass. Then so that can be the mass of the body. If here it can be considered as the mass of the object there, mass of the frame, reference frame is considered the mass of the body, then acceleration of the pseudo force is said to be the by this acceleration and the mass of the body, there is a force will be acting. No, that force is called the pseudo force, and that pseudo force will be equal to the net force acting on the body there. Net force acting on the body, while the reference frame is also in the motion with certain acceleration there. So then that is called the pseudo force, and this pseudo force we are going to discuss in the coming concept, that is the free body diagram there. Okay, free body diagram. So free body diagram. So free body diagram is nothing but it is the diagrammatical representation of the body in on which there is the multiple forces are acting there. Okay, so the forces which are acting on the body, multiple forces are acting on the body, so that can be represented by the diagram. So that diagram is said to be the free body diagram there. Okay, suppose here we can take the example of a person is standing on the floor. A person is standing on the floor. Okay, if a person is standing on the floor, then there are the multiple forces will be acting on the body there. So here the weight will be act the one force, weight of the person will be act here, and opposite to this the normal reaction will be takes place there. Normal reaction, this is a n. Normal reaction is nothing but the force which is acting opposite to the weight of the body and perpendicular to its surface is said to be the normal reaction force. Normal reaction force. So due to this reaction force, normal reaction force, the body can be balanced. Okay, the body can be balanced. Otherwise, it cannot be balanced there. It cannot be stable vertically. Okay, it may be fly there. Okay, that is due to the normal reaction there. And this will be the weight. Weight is nothing but what the product of mass and acceleration to gravity which is acting on the body there. Okay, so that is the these two will be equal. Whenever these two will be equal, the body will be at a stable equilibrium position, stationary. Okay, so then now it is then this whole diagram can be written by like this free body diagram. There is no all the objects will be there. Whole mass of the body is treated as here point size mass. Then the forces can be represented. What are the forces in which direction they are acting there? That has to be represented there. If you draw like this, then that will be the free body diagram. So the free body diagram is nothing but it is a diagrammatical representation of the forces acting on the body in the different directions there. Okay, that is said to be the, and even it can be shows the direction of the motion of the body, in which direction the acceleration it is, in which direction it is moving there, or it is moving towards the left side or right side there. So that all can be get to know by this drawing the free body diagram there. So to draw that free body diagram, there are certain rules we should follow there. Okay, so rules to draw the ray diagram now. Rules to draw the ray diagram. Sorry, rules to draw the free body diagram. Rules to draw the free body diagram. FBD. FBD. So first thing is we should identify the system there. We should identify the system. So we should decide the system whether the system has only single body or group of system of bodies are present there, or on which it is present there, on which reference frame they are present there. All the bodies are connected with any strings, or they are connected by contacted. Two bodies are contacted or three bodies are contacted. So we have to decide the system there. Okay, or we should identify the system, or decide the system. And second one, so we should recognize the forces. What are the forces acting on the system? In which direction they are acting there? Okay, the direction, in which coordinates the forces are acting there. So we should identify the next one. So recognize the forces. Recognize the forces acting on the system. Forces acting on the system there. Okay. What are the forces? In which direction the forces? Direction of the forces also we should. That is the recognition of the forces acting on the system. Okay. And next one. So the direction of the acceleration, the coordinates. So third one we should here. So the direction of the recognize, to identify. We should identify the forces. Identify the forces Identify the direction of the acceleration. Along the coordinate system. So which coordinate the system, along which coordinate, along x coordinate or y coordinate, in which coordinate they are the acceleration of the body is taking place, that we should identify that. And finally, so we should write the equations. Then write the equations of forces. Write the equations of forces acting on the system. Forces acting on the system or a body. By using the direction of the acceleration. Of the different bodies of the system. Direction of the acceleration, that's it is another direction of the acceleration. So these are the rules, we should follow that. Okay. So in the previous case here I have given here, no, this is a, so like that we should follow. We should identify here only single person is standing on the floor there. That is a system there, single person is a system. And here we can see the system, floor and the person is a system. And what are the forces? So we should identify the forces there. So always in any body, the force, weight of the body will be act downward direction and opposite to the normal reaction. This is a common for all the forces. Here only two forces are acting there, and there is no forces are acting along the x direction and y direction. Along x direction there, because there is no acceleration. The body is not, it is moving there. It is at stationary. So we'll get here. The forces, one is upward, that is a normal reaction, and downwards is the weight of the body there. Okay. So and there is no acceleration. No, here acceleration is 0 here. Acceleration of the body is 0. It is not moving along x-axis or y-axis or along both the axis. Along the coordinate system, there is no motion of the body there. So A will be 0 there. So acceleration of the body will be 0. So then now we can write the equation here now. What is the equation we can get there here? So the net forces along the x direction. Net forces along x direction is 0 there. Net forces along x direction is 0. And here along the vertical direction, what is the equation we will get there? Now finally we are writing the equations, that is, and vertical direction of the forces. So what are the forces here? Along the vertical direction, the forces acting here, that is a normal reaction is equals to, okay, or we can say normal reaction is equals to weight of the body there. So then we'll get here the final equation, N is equals to mg. So like this, we should write the equations. Okay, in the different bodies will be see there, different bodies. There are many types of the objects will be given here. So for all the objects, we should write the free body diagram there. Okay, so that is about the free body diagram there. So there are different types of the bodies will be present there. So if the body is here, suppose the body is at, a block is there on the table, okay, and the weight of the body will be act downward direction, and this is a normal reaction will be act here. Suppose here it is pulled by a force F there, okay, pulled by a force F there, okay. Then consider this is a smooth surface. If the surface is a smooth, then we'll get here. So free body diagram of this we can write here. The whole mass of the body is treated as small point, and weight is acting here, that is W, and here the normal reaction acting, and here the force is acting there, F. Yeah. So then this is a frictional force. The coefficient of friction between the surface and the block is 0. There is no force acting along x direction. Now here the acceleration, where the acceleration is acting here, along x direction the acceleration of the body will be there. Okay. So then we will be right there. So equation there. What can we write the equation here? So we can write there n is equals to m into z, and the force is acting. This is the mass of the body is there. Then from this we can write there mass F is equals to force is nothing but mass into acceleration. No? So this is two are the equations we will get in there. So because the whole mass of the body is moving along the x direction there. So those are the equations we will get it there. Okay, that is the free body diagram. So in the numericals, we are going to see the different cases of the bodies. Okay. So in the next concept, it is explained there. Already I explained the pseudo force and this. No. So here the examples are given there, non-inertial frames and the pseudo force. And in which direction this pseudo force will be acted there? In the opposite direction of the motion of the body. Suppose here the motion of the body is there along x direction or along the y direction, this pseudo force will be acted there. Okay. So then that's about the pseudo force, it has explained. Example for non-inertial frames here it is given there, accelerating car, merry-go-round, okay, and artificial satellite. So car going around circular path, okay, they are all the examples. And the lift is at rest is example for the inertial frame, and the lift is moving with constant velocity. A body is there at rest, okay, bus is there at rest, it is example. The body, we are moving on the ground, is move, this is the, so with respect to us the earth will be at the rest, no? So then we can say that is a person is moving on the ground, it is the example of inertial frames. Like that in the next synopsis it has explained there. So next one we are going to see here. So there are the different cases here, the lift is moving in the pseudo force, there are the different cases will be there. If the lift is moving up, okay, with certain acceleration there. So weight of this lift will back downward direction, mg, and the normal reaction will be there here, normal reaction, okay, n will be there. If it is moving up, then what will be the, so whenever this lift is at rest or it is moving with constant acceleration, we can say it is example for inertial frame. But if the lift is moving with certain acceleration there, with changing velocity, so then what happens there here? There is a pseudo force. Due to this acceleration, there is a pseudo force will be acted there. Okay, to apply here Newton's second law, we need to consider this pseudo force there. That pseudo force, how we can write that it is moving upwards, then the net force will be what happened then? Net force means normal reaction will be greater. So the net force can be written as here n minus mg, okay, is equals to, this is the net force, and the that will be equal to, pseudo force will be in opposite direction. Now we can write here there is the mass of the this lift and the acceleration of the lift there. Okay, so this will be the equation for the equation for whenever the body is moving along the vertical direction upwards, or we can say the lift is ascending, then we can write here n is equals to mg plus m into a, we can write there. So n is equals to m into a plus g. So this is the effective, this is the effective acceleration when the lift is moving with certain acceleration there. Effective acceleration. Effective acceleration. In the same manner, if the lift is moving downwards there, if the lift is moving downwards, then this will be greater now, weight will be greater now in this case. Now if it is moving downwards there with acceleration a, then this mass will be, means weight of the body will be greater than this normal reaction. So we can write here net force mg minus n, so that is equal to m into a, we can write. So from here n is equals to m into g minus a, we write there. So g minus a. So whenever the lift is moving downwards, so normal reaction will be m into g minus a, we can write there. Whenever the lift is moving upwards, we can write here m into g plus a, we can write there. That is the effective acceleration here, and this is the effective acceleration here. Okay. So there are the different cases like this we have. So while we are discussing the problems, we are going to discuss different free body diagrams of the different cases we are going to discuss, and different cases here we can see. And next one, suppose the body is moving, okay, the body is moving on the inclined plane, or we can write here Atwood machine here, Atwood machine is there. So If the body is connected by the two blocks are connected by the strings and it is placed over the pulley like this. So it is a pulley like this, and this pulley is suspended from the rigid support, and over this by the strings two blocks are placed. Then this is said to be the Atwood machine. Okay, the simple construction, pulley and axle, and the two blocks are connected with the strings. Then this is said to be this is considered here mass M2 and here M1. Okay, so then if M2 is greater, if it is placed like this keep on moving due to the inertia of the body there, they will be keep on oscillate there up and down. So then they will be move with certain acceleration there. Okay, so then acceleration equation will be there, that is a M2 minus M1 by M1 plus M2 will be there. So this one tomorrow we are going to see about this derivation of this one and tension. There are many different cases are there. We are going to discuss in the next class. So thank you children. Have a nice day.